Good afternoon and welcome everyone to today's ARPAS-UK webinar with TTP. The subject we are going to be discussing today is detect and avoid. Is it possible without weighing down drones with expensive sensors? We're delighted that Vidhya Sridhar from TTP is here to take us through this discussion, as this is her particular area of expertise. I'm going to share the screen and we will get going. If you could please keep your cameras off and your microphones muted. At the end of the session, we'll host the Q&A session, so please add your questions into the Q&A section and we will come back to them all at the end. Thank you very much for joining us, and let's make a start. So is that showing up okay then, Vidhya?
No, I think it's the wrong screen.
Oh, wrong screen. Sorry, apologies. Hang on, stop sharing. That's what I had to worry. There we go. View control and ensure that that is maximized. So there we go. So Dr. Vidhya Sridhar is Head of Autonomous Technology at TTP, and she leads the Autonomous Technologies Market Team, working on exciting technology enablers for safe and secure autonomy on the ground, in the air and in space. She's been deeply involved in the UAV and space sustainability sectors, very currently topical, and has engaged with various stakeholders to assess communication and safety subsystem offerings. Vidhya is an engineer with a background in digital signal processing and communications. And Vidhya, I am going to hand over to you now.
Amazing, thank you, Elena. So welcome everybody. I'm just going to check I can indeed control this. Can I go to the next slide? Yes, I can. Super. Thank you all for joining, and thank you ARPAS-UK for giving me this opportunity to present. I thought just before I dive into the topic of the day, I'll just very briefly tell you who we are. You might not know who we are. So TTP, we're a technology and product development consultancy business based just south of Cambridge in Mildred. Been around for 35 years, innovating in very diverse markets, from sort of healthcare to medical devices to deep technologies in aviation to novel energy and materials. We're about 250 scientists and engineers, very, very interdisciplinary, which is what enables us to go after very different markets. We do 200 plus projects a year. We have just the one site here in Cambridge, south of Cambridge, but we work with clients all over the world, ranging from startups to multinationals. And the sorts of projects we tend to be, almost going from blank sheet of paper, taking that through to an opportunity discovery, to transferring something to production and to manufacture. So quite big, large scale projects. As Elena said, I lead the one of the market teams within TTP focused on autonomous technologies. So sort of the areas that we're looking at where we want to enable autonomy ranges from automotive to aviation to agri-tech to mining. So quite broad in terms of the number of markets we're looking at disrupting. And the sort of capabilities that let us do that is quite deep expertise in sensing, sort of optics, using off-the-shelf cameras, stitching them together, to doing some fundamental optics development. We've done a lot of work in sensor reliability, sensor cleaning systems in the automotive sector, quite a lot of work in radar and acoustics and processing as well. Algorithms are sort of the bread and butter for almost all the projects that we do here at TTP, and this ranges from simple camera stitching to deploying a neural network in a very regulated sector. So done the whole lot. And the last pillar there is communications, as you might imagine. So we've got a lot of deep expertise and sort of heritage in that area, ranging again from SATCOMs to terrestrial, to 5G non-terrestrial, to bespoke communication systems development if the client has needed it. Very small summary, short summary of who we are, and then let's jump straight into the topic of the day. So we're here to talk about really the enablers of beyond visual line of sight, of which one of them is detect and avoid. The list I've got here is not comprehensive, but it's just some of the top ones that we're particularly interested in. So command and control, reliable command and control to a UAV, remote ID, enablers of remote ID, electronic conspicuity, and detect and avoid. So these are sort of some of the key enablers or essentials for beyond visual line of sight. And as we all know, beyond visual line of sight is the theme of the day for the UAV sector, is needed to unlock the true potential of the UAV sector. Very briefly, again, touching on the command and control side, I'll only do this one slide on that. We are doing a lot of work in that area as well. What you see there is actually a very small form factor terminal that we are developing that offers LTE as well as SATCOM for reliable command and control. This is a project that we're currently working on with Inmarsat. So we do other things in UAV safety outside of detect and avoid, just for your information. But detect and avoid is what we're here to talk about, and all of that is about how do you manage airspace conflict, right? Detect and avoid is not the first thing you would do. The first thing you would do is procedural. So that's what this image here is showing. If you work yourself from the right to the left, first thing you do is procedural planning, interfacing with air traffic management. Now, if that fails, you're looking at cooperative methods like ADS-B. Perhaps you have a subscription to a UTM provider who's funneling in data from other cooperative ground surveillance sources, for example. And it's if all of that fails, it's that last mile tactical deconfliction that we're terming here as detect and avoid, which is if everything else fails, how do I still see another user when you're flying? And just to also clarify, a lot of the presentation here, I'll be talking about the detect part of detect and avoid, which is the harder piece in our view. So it's worthwhile spending a little bit of time talking about what good means for this part of detect and avoid. What are the goalposts that we're looking at? And I think that the safety goalposts here vary a lot based on what type of aircraft, UAV that you're using, and where you're flying it, right? What is your use case? So I've very simplistically here broken it down into small and large, just for ease of presentation. So for the smaller aircraft, so maybe you're flying in uncontrolled airspace, doing sort of, you can imagine sort of urban cargo drone delivery, let's say. Standards like the ACAS-SXU that's coming out of ASTM International will likely apply. We're talking about detection ranges of sort of 1.5 to 2 kilometers, that sort of range. The angular rate accuracy that you would need to meet will depend on the speed and the capabilities of your aircraft. And there's some study on that as part of this ACAS-SXU standards, for example. Now, on the other side, it's quite different. We're talking about larger aircraft. It might be, like a Cessna, uncrewed Cessna, trying to do long range delivery, for example, flying in controlled airspace. So you have a very different set of standards that apply there. So DO 36387, for example, are coming out of RTCA. We're talking about much larger detection ranges, 4 kilometers plus. 4 kilometers really the minimum. People are talking about 5 kilometers really for larger, faster moving targets. So the safety goalposts are quite different, and the payload constraints, as you can imagine, are quite different as well. So I've got some numbers here, and some of these are based from talking to stakeholders in the space. So on the left-hand side, as you can see, quite size, weight, and power and cost constraints, and some of them a bit ambitious numbers, I would say. On the right-hand side, not so much weight and power constraints. Still a little sensitive to cost, but really the challenge there is the ease of commercial access and ease of manufacture for the large aircraft. So as we see it, the gaps in these two markets broadly are quite different, right? And this is where we started, talking to stakeholders, looking at what's coming out of the regulations and trying to understand where the gaps in the markets are. And why is this hard? This is hard because you're trying to find a sweet spot in this trade-off space that you see there. So trying to meet the performance you need, which could be range and the number of targets that you need to detect at the same time, the angular resolution that you might need to meet within a size, weight, power, cost, compute constraints, while still demonstrating aviation grade reliability. That's a hard problem. Which is why it's fun. We at TTP, we love fun problems like that. So what we did, we did some internal work last year, a very high level study, looking at basically what's possible, what's the art of the possible, and for us to really put our hands around the problem to see, can we really move the dial in terms of bringing about a disruption in the space. Just a caveat here that we did end up focusing a lot on onboard detect or detect and avoid, but that's not to say we fully understand and aware that a lot of the use cases could be addressed by, ground-based solutions or maybe hybrid solutions. And actually, this is part of a future study that we'll be doing as a follow-on from our current work. So what we did in our study is, looked at some of the standards, as I mentioned. We talked to several stakeholders to understand what are their payload requirements. And then we went away and basically thought about what's possible with different sensing technologies that are out there, primarily visual, acoustic, radar, and LiDAR. I think we very quickly ruled out LiDAR because just the range requirements just don't fit the bill in terms of a LiDAR solution. So the rest of the talk, I'll focus on the other three and share sort of high level insights on each of the sensing methodologies. So starting with visual approaches then, I think the top level summary that came out of the study is that it's definitely a promising approach, particularly for, sorry with abbreviations, I should have expanded that stands for low mean takeoff weights, so the smaller UAVs. So it's a promising approach for that category of UAVs and potentially a secondary classification tool for the larger aircraft. And we explored a couple of different architecture trade-offs as part of the study. So in the visual techniques, the main thing that influences the swap is the number of cameras, right? And then in turn, that's influenced by how you do certain things in your algorithms. So for example, how are you measuring distance, right? Are you doing a per frame measurement using stereo, or are you doing frame-to-frame measurements? Because that in turn influences, for example, if it's the latter, you could be using fewer cameras. What type of lenses do you need, right? Can your algorithm, the way you've designed your algorithm, can it get away with quite a low quality of lenses? How much angular coverage do you need? So you can imagine if you're using multiple sensors rather than a single one, maybe you can compromise on the angular coverage that the visual approach needs, for example. And then I talked about how the number of cameras is in turn determined by the number of type of algorithms, and the algorithm selection is in turn determined by, well, how much compute can you afford to have on board, and what is acceptable by the regulator? Because as some of you may know, I mean, having a neural network or a AI system as part of a safety subsystem, just justifying that to a regulator is hard. So and providing the tools to verify and validate that is quite hard. So we need to think quite hard about our software process and ensure that we use, this is the way we went about it. We tried and ensure that most of the blocks we could use classical methods where possible, and really we tried to bound the areas where we ended up using sort of more AI approaches quite in a quite small way. So what you see in the background, actually, you see, I don't know if you can see that video. I hope you can. That's one of our colleagues flies hang gliders, and this is from a hang gliding competition, and it's taken off a GoPro from the house. So quite a low range camera, and the approach we've used there is a simple frame by frame method. Well, I say simple, it's a bit more complex than that. It's using the frame by frame difference to detect motion. It's doing a good job of capturing most of the flying objects, but it's also making some mistakes, picking up some wrong things. The point of this is to show you methods where you don't need training data, right? And it's quite a classical approach. It's predictable in that sense and easily verifiable. So we try to use a lot of this in our software development methodology. And basically, our first level analysis, which comprised of looking at, well, what off-the-shelf cameras can we use, what off-the-shelf lenses can we use, what sorts of algorithms could we be using. So that sort of ground-up approach, we think we can come up with quite an attractive SWOPC. So I've put some numbers there. If you've looked at other off-the-shelf solutions, DAA solutions, I mean, I'm sure you'll be convinced that is quite different, quite disruptive in terms of the potential. And we think that with that we can bring a performance that's suited for lower mean takeoff weight use cases. Moving on to the acoustic methods. And the top summary there is we felt that it's unlikely to be a primary line of defense, but it could be an excellent sort of secondary assist to a lead sensor, particularly for the lower mean takeoff weight use cases. I'll elaborate sort of a bit of the thinking that led to that conclusion. The primary things that limit or enable the performance for acoustic methods are a couple. So what top one, of course, is obvious, is the number of microphones, right? How many can you fit in your or distribute in your UAV wing in the widest part of your UAV sensibly? What type of microphones are you using? What sensitivity do they have? The third one there is the most important one. How are you able to suppress self noise? So this is just, your UAV propeller noise, for example, and the wind noise. So the noise that the wind's creating just by blowing across the sensors. That is extremely limiting for acoustic methods. And of course, the minimum signal to noise ratio that's needed for classification. And the minimum SNR is in turn determined by the algorithm that you're using, which is a function of how much training data have you got for all the different types of intruders that you may come across in your airspace, and the ability to identify capsule features over time, for example, corresponding to the different intruders. So what you see in the background there, that image, is us having a play with some off-the-shelf data. I think this is from a helicopter noise source. So we were looking at this caption to sort of capture. You can see some chopping features there from the rotors. So if your intruders present themselves with some features like this, there's definite SNR gains that an audio system could bring, and it could be a very interesting assist in terms of classification for a lead sensor. So we made some, we took a sort of an example scenario. So in this case, for a light aircraft, that's sort of the typical sound pressure level that I've quoted there. And this graph that you see is a acoustic link budget. We have assumed in this case, I think about 32 microphones. We've assumed top class mics in terms of the sensitivity, made some good assumptions around how much path loss you typically have, and what sort of beamforming algorithms you could be using so that you have the right SNR gains. So, and we've also made some assumptions on what typical self-noise suppression that you could do, right, on the UAV, on the acoustic array. And what that graph is telling you is that if we think that, we need about 10 dB of SNR, let's say, for detection, you're looking at really like 500 meters range. Let's say even if we push that down to 0 dB, it's probably get you up to 1 kilometer. So not quite what we need. So which is why we felt that, you know, it's unlikely to be sort of a lead sensor, but it could be a very good sort of secondary assist for classification. But the really good thing is that if you already have a computer on board, maybe for a camera system, for example, the acoustic signal processing could very easily piggyback on that. And the rest of the swap is just free. So the numbers I've quoted there is for the scenario array I described just now. And you can see that's like negligible compared to the rest of the system. So the swap is almost free. And so it could be a very good sort of secondary tool. And then last but not the least, radar. And for radar systems, it's worth splitting that into two, thinking about it for lower mean takeoff weight and higher. For the lower category, it's probably you're looking at solutions in the millimeter wave frequencies to meet some of the SWAP-C requirements. I've said there that it's not a regulated air-to-air band, but there's some interesting news coming from the US and FCC, where they're licensing some new bands, particularly I think for emergency response drones. So yeah, some interesting movement there. That plot is from a simulation that we did. So you can see that's sort of the 76-81 gigahertz bands. We considered if you had a 30 centimeter antenna and a small plane target, right? What range could you get at a sensible SNR? And that's telling you at about 20 dB, if you wanted 20 dB SNR, you could get 1 kilometer of range. So if you could cope with something lower, which we probably could, we can meet the range, 1.5 to 2 kilometers range that's needed for the smaller UAVs. The challenge, I suppose, in the millimeter wave domain is keeping the power low and keeping the beamforming complexity low, right? And within the form factor needed for smaller UAVs. And this is again an area that we're working on. For the higher mean takeoff weight, so just a reminder, we're talking about detection ranges of like 4 kilometers plus, right? For those sorts of aircraft, we're probably looking at K-band and X-band, those sorts of radar solutions. And it's always useful to go back to fundamentals. I've just put up the radar range equation there, and what that's telling you is the green things are the parameters you can play with in a radar system. So you've got the transmit power, the transmit gain, the receive gain, the wavelength, and the noise figure. So if we're saying we need 4 kilometers at least, and let's assume a K-band operation, the numbers there tell you sort of the typical transmit powers, typical transmit and receive gain, and noise figures you would need to meet that. That's quite an aggressive noise figure, 1.5 dB. And so that's basically saying that you can't just take off-the-shelf COTS components and string them together. You'll need a custom RF front end, and you probably will need a custom antenna array as well to meet the sort of transmit and receive gains. So really the performance particularly for higher mean takeoff weights use cases is determined by what is the complexity of beamforming that's needed. You know, can it be digital? Can we afford that much power, or does it have to be hybrid? Can we use off-the-shelf parts as much as possible, particularly for the signal processing aspects? Can we leverage the boom that's happening in the 5G NTN space to our advantage? It's those sorts of things that we're looking at to arrive at a palatable SWAP-C. Clutter often comes up. We are aware that a lot of the solutions out there don't cope with clutter very well. And so having a good clutter strategy. So, you know, the most challenging clutter is takeoff and landing, when a lot of the Doppler and spatial signatures of clutter and targets don't look very different. So you have to have a different approach to that to cruise, for example. So having an appropriate clutter strategy. And the last one is, of course, where do you actually house that within the aircraft? Is it going under the wing? Is there enough room there? So that sort of integration to a variety of aircraft is also quite key for a radar system. So yes, I think I've probably already said that. Whilst talking through, is the challenge here is how can you build something that's built for the commercial market, because a lot of the radar solutions out there are either built for the defense, so extremely expensive, or they just don't meet performance because they've not really built for detection work, they've built for something else altogether. So we're looking at all of those architectural trade-offs that I've described to basically address that problem of ease of commercial access and cost. So the sort of, after we did all of this assessment, I think the theme that was coming out was that it doesn't feel like one sensor fits the bill, right? To really bring about disruption, we probably need to be looking at a combination. And actually some of the sensors straight away don't meet the requirements of some classes of UAVs. So for example, an acoustic solution, I don't think is relevant to a high mean takeoff weight UAVs. But even for the other use cases, each sensor has its pros and cons. So this is when we started thinking about sort of sensor fusion. What could sensor fusion potentially do? And what might the sensor fusion architecture look like? I'm not suggesting what I've got here is the answer. It's an example of how it might look like. So for example, you could have a camera array, a mic array, and a radar fusing. One of this is a lead, right? I'm not suggesting they're all, one of them is definitely a lead sensor for detection, but you would be fusing that to get your final detection and classification results, and then use your traditional IMUs and ADS-B to further estimate position and motion, and then initialize track. So what we'll be looking to do, and depending on the use case, choose sensors that complement each other in the information they provide, and also just fuse them because they're providing independent readings of the same information. And so you're getting SNR gain, performance gain due to that. And this is what we have now started exploring. And we think the potential for this is big. So for the low mean takeoff weight, where we think the current state of the art is, it's not quite meeting performance, it's not quite meeting size, weight, power, and cost, and reliability, performance in all kinds of environments. We think sensor fusion can really move the dial in terms of being able to use lower cost sensors, and hence bring the size, weight, power, and cost down, and also improve the reliability, just to the fact that it's multimodal. Oh, sorry, there's an error in that slide. It should say high mean takeoff weight. So where we think on the higher mean takeoff weight, where we can sort of improve the dial is where current solutions probably meet performance, but they're built for the defense, so they just aren't suitable in terms of cost, and they're not sort of suitable. They're not easily accessible by the commercial market. We're thinking of alternate, fundamentally radar architectures, but also we're thinking of architectures where the radar could be simplified by other sensors so that we can bring the cost down, and we can we're trying to look at architectures where we're using sort of scalable off-the-shelf parts as much as possible so that it's easily accessible by the commercial market. Right, and I think that sort of leads me to the key takeaways that I would like you to remember from today's session. So even if you've forgot a lot of the detail that I was talking about, I would love for you to take away some of the stuff on this slide. So I think what we're trying to say, or what we believe in, is that we can achieve a sensible SWaP-C and performance, particularly for airborne detect and avoid. And we think sensor fusion could be the key to do that, right? And why sensor fusion? Because we think that enables you to perform in varied environments, but more importantly, it helps you to use, it might enable you to use lower resolution sensors. We're absolutely saying that there isn't one solution that fits all. The solution is going to be different, likely to be different based on your use case and your UAV type. And the fourth bullet there shouldn't come as a surprise. The route to get to an acceptable solution is, work in phases, proceed in stages, and sort of work with all the stakeholders, take them along the journey. And actually today's webinar is part of that. Is what we're looking to do is invite feedback and conversations. We want to work with the regulator. We've already started conversations around that. We think one of the key things to get a solution out in the market is be able to manage if AI is needed and if it is bounded well in the solution. And people often talk about flight hours. Yes, it's important, but we think also to really up the reliability of solution simulation also has a very important role to play. So we're also sort of investing in good simulation tools to be able to do that. And we're looking for partners and conversations, right? So we're talking to several people and sort of building a interested stakeholders group, I suppose, comprising of regulatory partners, UAV OEMs, we're talking to sensor subsystem providers as well as go-to-market partners. And what we want to do, and actually we probably will start in a couple of months now, is build on the study we have done so far, and to actually solidify what sort of sensor fusion architectures we are deciding to take forward. And that will be determined by what fraction of UAV use cases are we able to access by going with a particular sensor fusion architecture, because that directly influences the return on investment, doesn't it? So partnership can mean several things for us. I've put some examples there. If maybe you already have part of the solution, maybe you're developing a sensor subsystem, that's interesting to us. Maybe you're developing other elements of UAV safety, so you may be interested in a joint at the hip sort of partnership to bring a safety solution together to market, for example. Maybe you may be able to provide resources in terms of data, airframe, drone highways. Partnership for funding, always open to that conversation, of course. And maybe you see yourself as a go-to-market partner. And outside of all of this, I'm always happy to have a chat, really. So if you have any questions, any feedback, please feel free to reach out. Well, you have my email ID. You can also, that email ID is wrong. Okay, I have to correct that. But you can also find me on LinkedIn. And I think we have time for questions now as well. And if there are, I'll answer them to the best possible way I can. And if I can't, I can always take them offline and respond later. Thank you. Thank you for your time.
That's great. Thank you very much indeed, Vidhya. That was a fascinating look at the detect and avoid side of things and what TTP's been doing. We do indeed have some questions that people have come up with already. So let's find those, and please do add some as we're going along, everyone. So the first question is, why had Zipline gone acoustic and not camera with a 2-kilometer range?
Excellent question. I think it's purely because of the attractive weight that it can offer. Now, I have looked at their I think their lead perception engineer talking about the solution. And yes, I can convince myself that they can probably see like a Cessna 2 kilometers away. I cannot convince myself that they can hear a hang glider that even a kilometer away. So whilst it may be an interim solution, I think it will need to evolve, in my view. That's my personal view.
Mm-hmm. Great. I have got a comment saying, sounds like this is counter UAS. I think I'd probably also argue that it's actually a system for detecting and seeing who's where within the airspace. I think it's probably also the air traffic management side of things as well, or unified traffic management. Would you agree with that, Vidhya?
Yeah, absolutely. And interestingly, actually, a lot of the radar solutions that are now being tried in the detect and avoid space were actually counter UAS before, and they're being repurposed for DAA. and well, because of that, they're facing clutter problems, because it's not counter UAS is looking up, isn't it? So it's not designed for DAA. But yeah, I think there is a potential to use some counter UAS solutions for DAA, or repurpose some of that for DAA, I think.
Okay. The next question, is there a preferred sensor type to minimize the amount of sensors needed for 6-directional DAA?
I don't have an answer to that today. So I think what we're almost saying is there isn't a single sensor that can do that. With our view is, so for example, we know of solutions like iris automation. You could use a camera-based solution. You could use multiple cameras, but very quickly adds weights. You could use multiple radar, again, very quickly adds power. So we think to get to that sort of 6-directional, 360-degree angular coverage is what FAA is saying they need. You probably need multiple different modalities, sort of capturing, maybe one of them is covering for each other in terms of angular coverage, or maybe it could be a split, could be one of them is doing detection and the other one is tracking, for example. So yeah, I don't have an answer to that, I'm afraid. And that's part of, we'll be looking to answer exactly that. What combination of sensors do we need for what type of UAV use case in the work that we're hoping to do soon.
Thank you. Very interesting talk, thank you. What do you think is a reasonable timeline for getting a robust DAA?
That's a hard one. It's not an easy problem, right? And it's going to take, what we're talking about is a multi-year project, right? And I think we're just starting to scratch the surface of that. With a disruptive solution like this, we could probably get a proof of concept in a year, but a certified solution that's undergone rigorous testing, we're talking about 2 or 3 years. But we'll be bringing, what we want to do soon is do proof of concept so that we're bringing a regulator and other stakeholders on the journey, so that we're sort of setting ourselves up for success when we actually have a product or a technology in a couple of years.
Thank you. Well, that sounds a very realistic timeline. How much, if any, discussion with the CAA did you have during this project? Do they have a view on utilising these technologies to enable unsegregated BVLOS?
I'm glad somebody has raised this question. I don't know if Thomas Bragg is part of the CAA. If you are, I'd be very keen to talk. So I have made the CAA aware of this, I suppose, and we have been in constant comms with them. But I'm almost looking for feedback and I haven't gotten yet, is the honest answer. So if you have roots in, or if you're able to help us get roots in, I'd be all ears.
Okay. I'm sure we might well be able to help on that side of things as well. So we can talk again at a later date, Vidhya. What's the key difference regarding the sensors for electronic conspicuity and DAA systems?
Well, I mean, electronic conspicuity that's more about making yourself known. So that's an active transmission. We're talking about systems that will catch even those who are not actively transmitting, who may be covered for legal reasons, or who just can't afford to be conspicuous because, well, if you're a hang glider, maybe you don't have to be conspicuous. I don't know. Or you're just not, you're in an airspace where you're not supposed to be, or you're a bird. So I think it's two very different things here. Is electronic conspicuity is talking about cooperative mechanisms, and we're talking about catching or being able to detect an uncooperative intruder in airspace.
And as you rightly say, there are environmental things in there as well, like large birds. Thank you. So for the small, lower than 25 kilo UAS, do you see any onboard detect and avoid apart from ADS-B being realistic, both in terms of price and payload penalties?
I think the answer today, well, we've done a high level study to answer exactly that, I think, to sort of say, can we do something in that space? And I think we've come out of that saying yes. And we're going to build on that. And what will move the dial, in our opinion, is sensor fusion, right? To meet that sort of very stringent SWaP-C restrictions.
Okay, that's great. And our last question currently, so do please keep them coming. There's some great questions coming through, and I'm much enjoying this discussion. Companies such as IRIS have abandoned airborne DAA. Also, what about RF detection? Finally, how much engagement has taken place with the GA community on this whole area?
Yeah, so that, yeah, the IRIS question is very interesting. So yeah, they seem to be refocusing a lot on their ground-based DAA solutions. This is a very hard sector for startups, as you can imagine, right? If the regulations aren't there, and so UAE OEMs are asking, well, I'm not yet forced to do this, so why should I do it? But they know they have to do it at some point. So it's, unfortunately, I think, I have spoken to the CEO of Iris Automation several times, and he's still confident about their airborne solution. It's not that it's been abandoned, it's still there. Those who have, the customers who have bought it are still being served, and their view is it is going to come in a couple of years. Startups don't have deep pockets, so they have to serve the here and now. And we are talking about a problem that is coming or where you need a solution in 3 years, but we're talking about it now because you need to show what's possible now to influence regulation, so that you have a solution that's sensible to the market in a couple of years.
Yeah.
And RF detection, yeah, that's interesting. Yes, we are. So I haven't talked about that today, but we are considering that as well, because that might as well be a very interesting modality to add in. And sometimes that's almost free, isn't it? Given what you have on other sensors that you've got on your aircraft, adding that in is definitely a element we're considering. How much engagement has taken place with the GA community? I don't have inroads there. We don't have inroads there, so not us directly. But my hope is that we're talking to OEMs, we're talking to regulatory consultancies. As I said, we're trying to talk to the CAA, and my hope is that they will take that forward and influence and get feedback. But again, I'm all ears if you've got roads in and if you're able to make introductions. I would very much like to hear their feedback on this.
I'm sure we can probably help there too as well, Vidhya. And do follow up with me again on that. Well, that seems to be the final question at the moment. I'm going to give everyone a moment or so while we to think up more. And as I say, I've much enjoyed this. The questions have come through really quite thick and fast in comparison to occasionally. I know that Annalise Scalieres, our CEO, is here and would like to add some information into this. So I'm just going to add her in. Hang on one moment. Annalise, have I added you correctly? I think you're in there as me again, but there we go.
Oh, sorry about that.
Don't worry.
Good afternoon, and thank you. It was extremely interesting, and it's really refreshing to go back to technology, actually, to start and solve the problem. And on my end, I think it's a great idea if we could have onboard DAA, because, put it bluntly, I guess it would be cheaper than having a complete ground network. So if there can be a complement or on board, that would be really a great piece of technology to add to the ecosystem. So I wanted to hijack, in a way, for a few minutes this webinar, but actually is for a good cause that is very much related to what we've just discussed. As ARPAS-UK, we're a member of a form of high-level group led by the DFT and industry. And the purpose of that group is to develop a joint strategic roadmap for the UK, for the sector, together with government, the CAA, and different industry players. And as part of that activity, we think it's time to engage with our members on literally expertise, because we've gone through the phases of agreeing on a vision and a high level direction, sense of travel, but we think we're coming now to a point where we do need more expertise, and typically this is expertise. So members, we will be in touch shortly to call for expertise. So the two topics to be confirmed, but the two topics will be, on one end, let's call it the UAS, and the strategic outcome is routine BVLOS UAS operations in shared airspace. So DAA is right on the topic. And the second area is a piloted eVTOL. So please, members and non-members, if you would like to reach out, do reach out as well. But stay tuned, please, so that we are in a position all together to provide the expertise required to that unique opportunity to shape the industry. Thank you, Elena, for letting me having that hijack.
It's okay, no problem at all. As you say, it's for a very good cause at the moment and has given people a chance to add more questions, or rather they haven't at the moment. So I'm going to say that we will close the Q&A section now, and I'm going to thank Vidhya Sridhar for starting this really good conversation. I know that there's a lot to take away from that. Vidhya has shared her contact details, and again, I will post the link, the recording link to this later on this afternoon, possibly tomorrow morning actually. And I will ensure that everyone who's registered to attend receives the link, as well as Vidhya's contact details if you want to take the conversation forward. Thank you very much for attending, everyone. We're delighted to have you all here today, and please keep an eye on the website for details of more CPD webinars coming up. I think that's it for the moment. We've got some great, really exciting ones coming up in the autumn. Again, please do get in touch if you'd like to discuss anything else within the, sort of the drone industry side of things as well, whether that's membership through to regulations and end user cases. So thank you, Vidhya. Thank you very much indeed, and brilliant, well done. Thank you very much.
It was my pleasure. Thank you so much.
Okay, and I'm going to end this now. Thanks very much for attending as well, everyone. Goodbye.